Hi everybody and welcome to our monthly buzz on quantum computing. My name is Sally Ann Williams and I'm the CEO of Cicada Innovations. Without further ado, I'm going to give you a couple of quick housekeeping notes and we're going to get into it today with our panelists and get straight into a conversation. One thing I want to do before we introduce them is to just acknowledge the sponsors of our event today. The ARC Centre of Excellence for Engineered Quantum Systems, EQUUS, and the Australian Quantum Technology Forum. Great places to go to if you want to know a little bit more about what's happening in Australia. So with that, let's introduce our panelists. First up, at IBM, Dr. Phan drives quantum education. Prior to IBM, as part of a postdoc and PhD in experimental particle physics, Anna worked at CERN. So welcome, Anna. It's great to have you here today. Give us a wave.
Thank you, Sally Ann.
And with your great big quantum computer in the background. I love that. Marcus, welcome. It's fantastic to have you here. Marcus co-founded Quantum Brilliance in 2019, building quantum microprocessors that promise to transform the future of computing. And if you missed it, there was some exciting conversation in the press yesterday about how far they've come and where they're going next. And I'm pretty sure we'll be able to get Marcus to tell us about that today as well. So Marcus, it's great to have you here.
Wonderful, Sally Ann. Thank you.
And last but not least, David, welcome today to the panel today. David holds a joint position with Microsoft and the University of Sydney, where he's principal researcher and the director of Microsoft Quantum. Hi, David.
Hey, thanks for having me.
Thanks for being here. All right, let's get into it because I really want to know when I'm going to get my quantum computer, what it is, and all things quantum. And we're going to break it down a little bit barbecue style. So I kind of like to say this because I'm not going to assume that everybody watching online today is a quantum physicist, because if there are, then we've got a lot of them engaged with us, and you probably all want to find jobs with the people on the panel. And I'm sure they're interested in connecting with you. But for those of you who are not a quantum physicist, for those of us that didn't do physics beyond year 12, or maybe dabbled a little bit after that, but really didn't get there, let's break down what is a quantum computer and why it matters. So Marcus, my first question to you, can you give me the barbecue explainer, the conversational tool that I can use with my parents, my aunties, my uncles at a barbecue where I already struggle to explain what I do running a tech incubator about what a quantum computer is? How do I do that?
Yeah, sure. Happy to attempt that. I'll do my best. So how I'd explain to my parents is that a quantum computer uses physics that current computers don't yet exploit. And that physics enables you to represent information in an entirely new way and to manipulate it much more efficiently. And as a result, quantum computers will allow you to do certain computational tasks, the ones which are very difficult on current computers, much faster or much more accurately. And the way it does this, the way it works, is that it replaces the fundamental component of a normal computer, a bit or a transistor in terms of its real device, and replaces it with a qubit. And a qubit is a quantum system now, which instead of being 0 or 1, can be a combination of 0 and 1. And when you start adding qubits together, you can encode further information in the correlations of the zeros and ones of the individual qubits. So you get this ability to encode information, a great deal more information. And because it's encoded in less, you can then efficiently manipulate that information using fewer resources to do so. And so what can these qubits be? These qubits can be atoms, or they can be specially engineered loops of superconductors. They can be photons or other sorts of elementary particles. Anything that you can engineer to exhibit these quantum phenomena of superposition, which gives you the combinations, or entanglement, which gives you that ability to manipulate correlations. How did I go, Sally Ann?
Well, you had me in the first couple of minutes, and then when we got to the ones and the twos, I started going down binary and started thinking about actually sitting there and coding. But that was actually probably one of the best descriptions, I think, to understand what a quantum computer is. And also the fact, I love at the end that you actually kind of talked about that there's different ways of building a computer without getting into the details of that yet and the depths of that. But there is different ways. So that was pretty good. I would definitely take a recording of that and just play it at the barbecue, I think, to make sure I don't get it wrong. I think the next question that I have, which is for Anna, and I'm going to throw this open to the panel after this as well. I think, Anna, this is going to help us with, I think, the critical question for most people. So we've heard a little bit about what a quantum computer is and a little bit about how we might think about building one, but we'll come back to that. What's it good for? I'd love to kind of hear from your experience. You've obviously been in this space for a while and you're looking at the applications of quantum computing. Why should we get excited about it? Because I think sometimes the what is cool, but the why is even cooler, and it drives people to go, I want it now. So give us your best inspiration.
Sure, Sally Ann. So I just want to step back as you're asking that question. So some of the world's hardest problems require extremely complex computations to solve, and ones that today's most powerful supercomputers cannot handle, and we believe even future computers will never be able to do them. Quantum computers, because they compute in this fundamentally completely different way by applying the laws of quantum mechanics, this makes them vastly more efficient at performing specific advanced mathematical operations. Apologies for the 3-syllable words I just said. So these advanced mathematical operations are like those required for things like simulations of molecular reactions, for optimization, for machine learning, or financial modeling. So these are applications which are used in the business world.
So just to build on that, what are the probably, I really like where you're headed, because whenever you sort of start talking about the business world and finance, and you're talking about molecular sort of discovery, you're starting to touch on two areas which Australia gets really excited about, I think, health and finance. What are some of the specific areas you're seeing sort of the greatest, I guess, emergence of quantum computing being put to use? And I'll throw that to you first, Anna, but then over to the guys as well to chime in.
Sure. So we see sort of 3 areas of near-term interest for quantum computers. So the first one is around quantum chemistry simulations. And this is really because if you look at how current high-performance computing simulates chemical molecules, they can see that even if we build larger and larger and larger supercomputers, the molecules they'll be able to simulate don't get larger as quickly as we need them to. So we're really interested in seeing how to use a quantum computer to simulate those larger, interesting molecules that we know we won't be able to simulate on classical future computers. So that's the first area. Another one in a similar idea is financial modeling. Mm-hmm. So the same similar problem. Yeah. And another area is optimization and trying to understand data that we have. So these problems scale a certain way on classical computers, and we know that the scaling of classical computers won't be as fast as these problems scale. So we're really interested to see if we can use quantum computers to solve these problems in the future.
Great. So you're talking about the future. David, what are you seeing right now? Is there anything that you're seeing that quantum computers are, really realistically being able to be applied to right now? Or is it still that distant horizon? And which areas are you seeing the most application?
Well, Sally Ann, I want to give you a honest answer, which for me is really motivating. And that is to look back in history and ask the question, how did people feel and what answers did they give panels when they were panelists in 1945, and digital computers of the kind that we now, take for granted and built economies around? What did people think those things were going to be useful for, and how effective are we as a species at predicting the future and understanding where technology goes? So while I was listening to Anna talk, I looked up a quote. So this is a quote that I want to read to you from John von Neumann in 1945. And if you don't know who John von Neumann is, It's harder to find somebody that is more knowledgeable about what it means to compute and what is computable, what is not computable, what might be computable in the future. He's the guy. And so in 1945, when asked the question, what are computers good for? What's this machine or device you're working on going to be good for? He said, and this is the quote, the projected device, or rather the species of devices of which it is to be the very first representative, is so radically new that many of its uses will only become clear after it has been put into operation. He goes on to say that the uses which are not or not easily predictable now are likely to be the most important ones. Indeed, they are by definition those which we do not recognize at present because they are the furthest removed from our present sphere. In other words, you have to build it, and once you have it, its real use will become increasingly clear. And there are so many examples over history, looking back in history, where we've seen that story played out with technology. We know, as Marcus mentioned in his nice description, we know that quantum computers are based on fundamentally different physics, physics that we currently don't exploit. It is incredibly difficult to imagine that new physics won't also give rise to new applications. And also not surprising that we have a hard time envisaging what those applications are, because there's nothing we can point to in our regular, technology space that is currently using those. So I'm not going to give you a list of possible algorithms. I think it's much more interesting to think about what we haven't even yet imagined.
I really love that. And I actually love that quote and that phrasing. I think this is the big challenge, both the challenge and the opportunity for us globally, but particularly in the Australian context, when I think about Australia's adoption of technologies and when we're early and when we're late. And it's been really interesting if I kind of extrapolate what you said and take that as a parallel, last year during the pandemic, the number of businesses that digitized, they went fully online and in the cloud. And I'm using my quotation marks, kind of giggling a little bit inside, because it's kind of like that's where I've been living and working and breathing for so many years, and it's the norm for me, and working in this kind of environment has been just what I've done. And for so many of us in the tech sector have been like that for years, but it's like there was a population shift and a transition culturally to a kind of much more digitized economy and a way of working and an understanding of things. Do you think, so do you think based on the sort of, what you've just said, is Australia ready to kind of jump in and start going on that journey? Because I think, and with the parallel of, the fact that we're close with quantum computers, it's so close, and yet there's still so close yet so far a little bit from everybody having something accessible in their pocket, sort of. What's the barrier to adoption, do you think? For Australia, what do we need to be cognizant about it? Because I do feel like we need to get people excited to come on this journey with the work that you're all doing.
Yeah, so maybe I'll jump in first there. It's a hard one, because what we're seeing, I think, at the moment globally is obviously a transition of this technology from basic concept work going on in academic labs at universities, now a big transition to industry. And you've obviously got a number of people here who are deeply involved in large companies that are pushing this technology. But it is not yet, in my view, solely in the domain of the industrial, program. It's very much still in this discovery phase, where the academic laboratories and environments bring so much, and we have to have both. We're trying to actually build, I think, out an ecosystem. And to come to your question about Australia, I think Australia is uniquely positioned in a lot of ways to sort of walk this fine line between that academic side and industrial side. But we need students and serendipity and mistakes, and I didn't like my supervisor, so I did the opposite, and look what you have. One needs that as well. We need the industrial muscle, the capital, the ability to sort of leverage all of the deep relationships that come with large tech companies or medium tech companies and so on, to actually go out and build something or engineer something that is very challenging to do in an academic small lab. So it's both, and I think Australia is well positioned to continue to find that balance, so long as we do adopt a mentality that this is an international endeavor, we have to play on a global stage. We aren't in the mode when it comes to quantum computing, in my view. This is not the Hills hoist. It's not going to be an Australian invention by Australians for Australians in Australia. Lock it up. That's just not going to work. We have to participate globally, and I think bring the action back into Australia, building capacity in Australia, but very much on a global stage. And to the extent we can do that, I do think we can succeed.
That's great. Thank you. Marcus, you are obviously building a quantum computer. What's your views on this? And you're in Canberra, you're in the ACT. There was a great announcement yesterday. Do you want to tell us your perspective on this?
So I certainly can, but I might offer two different perspectives. So in one role, I'm a co-founder and chief scientific officer at Quantum Brilliance, where we're building quantum computers, which have a particularly different role and set of applications to the technologies being developed by other companies. And it's this idea of a quantum accelerator. And I can talk about that and talk about how we're seeking to discover applications with partners and also customers, and also the types of needs that we're already solving by selling to customers who have specific needs. But I can also offer the perspective, because I work within the Future Land Warfare branch of the Australian Army, and the Australian Army has created a roadmap, which it will release later this year, most likely on the 20th of April, and has already launched a process called the Quantum Technology Challenge. And from that perspective, I can offer you how a big organisation like Army thinks about quantum technology and how it's approaching quantum technology and how it seeks to gain an advantage through it. So I'll offer both, and I might start with Army first. So Army's premise is perfectly in line with that von Neumann quote that David, thank you very much for giving us that. Army's premise is the most disruptive and highest value applications of quantum computing are yet to be discovered. And that advantage lies for Army in being the first to discover those applications and to prepare and know how to use those applications. And most likely they will change how Army operates. So it's not just a matter of thinking about taking a technology off the shelf and making Army, the way Army currently operates better. It's probably going to fundamentally change different aspects of how Army works, particularly when you join it up with robotics and autonomous systems, which Army is in the process of adopting. So the way Army is thinking about approaching quantum technologies is very much work, and that is engage the industry, engage the academic sector, get them to test and validate applications and iterate until you discover those applications. And be the first to do so, and then work out the implications for how Army is designed and its operations. And if I was in a corporation, that would be my similar view. Advantage for me right now is finding out what to use quantum computers for and how it's going to impact my business. And I will then get a first mover advantage in transforming my business and gaining the value from quantum computers. And so if you are a member of a corporation, I suggest look to what Army is doing, see how it goes. And if you like what you see coming out of Army and how it's evolving, then maybe think of starting programs similar to that in your own business. Talking from Quantum Brilliance's perspective, so we joined with Pawsey Supercomputing Centre last year to create this innovation hub. And now we see on Friday the launch of the Pawsey Pioneer programs, where we've brought together academics, quantum software startups, as well as established software companies to develop applications for various parts of industry. One is doing it for defence, doing advanced image and signal processing for defence. Another is building an application for the aviation industry for optimising logistics change. And that could be directly translated across to Australia's mining industry, where if you look at iron ore, logistics is actually the #1 thing that holds up our iron ore production and sales rather than digging it out of the ground. And then another is looking at finance. We've got a healthy finance and investment ecosystem here in Australia. And a third is looking at advanced scientific applications of quantum computing. So this sort of hub where you bring together a hardware provider, software and software developers supported by national infrastructure, being the Pawsey Supercomputing Centre, and then drawing in industry and science is how we can get this cross-pollination and this adoption and understanding and discovery applications. So that's my 2 cents.
I love it. That was actually really well phrased. And I think if there's any industry folks watching out there now, that first mover advantage of getting in and actually understanding it, you know, it speaks to the background that I had pre sort of, you know, Cicada Innovations, certainly here, but the background at Google, it was always about get involved, do it, build it, and figure out what you're going to use it for down the track. But if you're not there, you're always playing catch up. And I'd love to hear from your perspective. You know, you've got a research background, you're in IBM now. You know, what do you sort of see happening here, and what can you share with us?
Sure. So I think, like with any emerging technology, one of the hardest challenges is making it accessible and easy to use. That's why, like, that's an important part of the IBM mission, to make quantum computing available to everybody. And I'm part of the team that develops that educational content for our clients and the wider community. We really believe that open source access and adoption is how we're going to have an ecosystem of developers, scientists, educators, and professionals across different industries, and they'll learn what quantum computing is, understand how to use it for their industries, and hopefully come up with those new and exciting applications that people who build the computers can't come up with themselves. And really scaling a global community is key to advancing quantum computing for science and business. Seeing what other people are doing and building off the shoulders of others is how science works.
So what do you, I mean, I love the fact that education is part of this, right? I think you've all said it in different ways, that education has to actually be part of the journey to figure out the application side of it. And I think business education and community education is, I mean, it's a reason we're doing this webinar, right? So what are you finding works, what works in that education process? Where are you seeing where it resonates with people and they kind of get engaged and it becomes more than just sort of an intellectual thing? Is there anything that you can sort of share with us of that sort of where you're seeing the greatest success in that program?
So it really depends. It's a really hard question to answer, because obviously different areas of the community need different types of incentives and different types of education. So for example, we're collaborating with the University of Melbourne, who have come up with courses at undergraduate as well as graduate levels for people with any technical background, so not just physics. So, and that's really targeting students who are interested in the technology, but they don't have that physics background.
Okay.
And then for a wider community position, we created a whole set of videos and online textbook and materials like sort of targeted to that developer community, people who want to self-learn and understand what quantum computing is by themselves. And then of course, for our industry clients, we sort of tailor workshops and materials to those audiences. And it really depends on what people are interested in, right? You've got your deep technology people working at your banks or your airlines, and they just want to know how the technology works and get their hands dirty and code. Mm-hmm. And obviously the more business people want to know, how can I use quantum computing to solve my business problems? And so it's educating both those sets of people, and then getting them to work together from the technology side as well as the business side to solve a problem of interest at the actual company, as opposed to, oh, I've got employees playing with quantum computers on the side.
Yeah, no, that makes absolute sense. Then I'm seeing like quantum DevRel role coming in the future to Microsoft, IBM, and Google. They probably already exist, I have to say, by the sounds of it. I want to flip the question a little bit back to my quantum computer that I want to have. Marcus, you've touched on it, and David, actually all three of you have touched on quantum computing and the differences in there. I'd love to kind of step back a bit and sort of saying, there are different pathways that the tech companies are going. Marcus, you're doing something different at Quantum Brilliance. Which quantum computer, this is not on our scripted questions, but I just want to, ask this one. Why go down the pathway of different methods of building a quantum computer, and what are the advantages and the disadvantages to some of the different avenues that you're seeing pursued. Now that I know that I've sat around a table where people were debating this one day, and I've got to admit I tuned out after a point because I didn't quite grasp it. But I'm really intrigued by that because it is a different pathway, you know, Marcus, that you're pursuing that I think that others are. Talk us through that process, and David and Anna, please feel free to chime in as well, because I'm not nuanced enough on the difference between what IBM and Microsoft and Google are doing in this space either.
Yeah, sure. So Sally, I can kick off, and I dare say Anna and David will all have opinions here on it, but I might have a slightly different view of the world, and I'll be interested to see what Anna and David say. So my view is that the future is heterogeneous. The future is different technologies performing different roles. And the idea that there's going to be one winner is completely false and ridiculous to me. And that's because the different quantum computing technologies have different strengths and weaknesses, and they're better suited to different roles within the whole computing network. Mm-hmm. And so, for instance, you can think about superconducting computers like what IBM and David are involved in. They are very good mainframe devices. These are things that you know how to engineer, you can scale them, it's hard, but they're doing that work, and you can make these large mainframe computers like that. But then you have a look at other technologies like photonics and trapped ions, and they could fulfill a very different role. They could also do the mainframe role, but they could also do a distributed role. And that is where you can now place these around, you potentially can get them to communicate with each other, and you can think about a computing network with those sorts of devices. And then us with Diamond, we're occupying another part of that piece, which is we are very much about making compact, robust devices that are specifically designed to accelerate particular tasks. And so we occupy the world of living at the edge in satellites or in other sorts of mobile platforms, or living in massive parallelization. So being inserted in data centers alongside the classical computers, which are in all those racks and these sorts of things. And these different technologies will fulfill different computing functions. They'll be used for different applications and these sorts of things. But I think it's also fair to say that right now, we're also not so certain which technologies are going to really work.
Yeah.
You know? And so that's why there's such diversity. And it's also important that it's also valid to explore all these routes, because some will come to dead ends and others won't come to dead ends. And we're still in that emergent phase.
Great. Anna, what's your thoughts on this? And then we'll go to David.
I want to echo that. So like pulling a leaf from David's book, if we go back to the early beginnings of classical compute with using electrical relays and vacuum tubes, right? That's not what we're using today to talk to each other, right? We're using silicon semiconductors, which didn't exist at the time, right? So we know we want to build something that can create a qubit, and we have a variety of technologies that we're playing with now. And different experimentalists will tell you theirs is the best, or certain ones are good for some things and bad for others, like Marcus was saying. But it is really too hard to tell. I believe it's too hard to tell 50 years down the track what will be the ubiquitous quantum computer, if there will be one, or if we'll be using different technologies for different applications.
Great. David?
It's a topic that I will rant about for some time, so we need some timeout signal there. Sally,
okay, gotcha.
Can you cut me off on that one? Look, there's so many interesting aspects to this question that intersect, obviously, the scientific, the engineering, but very much also about, what is the business model here? How much patience does a company have, or how much patience does shareholders have? I agree very much with both what Anna and Marcus have already said. So without, emphasizing those points, maybe to take a few other issues that one has to consider, not that I necessarily align with them, but if you were to say to the leadership of a large company, we don't know how to do it, we have no line of sight to a large scalable machine that is actually going to be useful, but we're going to try and build something anyway that might go nowhere. I think your budget will be pretty small. So you might then fall into that problem of, well, the reason we didn't go anywhere was because our resources were pretty small. And so there is this weird sort of thing that you see across, I think, the whole community at the moment, which is big ambition, some line of sight, maybe, just a tiny line of sight to a machine that starts to get into territory where it may be useful and useful for business. Everybody knowing full well that it's going to be a complicated journey to get there. We may not end up being exactly the destination we aimed at, but without that line of sight, it's really hard to then build something that's large enough in terms of the resources to then meaningfully do it. And so there is a bit of a chicken and egg here. And I very much agree that the world does not yet have a quantum technology that covers all bases, that scales. I don't think we know how to build a quantum computer, if I'm really honest. I don't think the world knows how to build a scalable quantum computer yet. We have various proposals, various hopes, but it's going to be an evolution. At the same time, part of what's going on here is testing out, are our assumptions, at least in principle, do they allow for these machines to exist? And if you can't articulate a story that takes us from today through to a scalable machine that's useful, if we can't even tell what that story is, putting to one side the path we'll take, whether it's really realizable, engineering challenges, all the rest of it, we can't even tell that story, we're in big trouble. So we need to be able to tell that story, I think. And yeah, it's a challenging issue. I agree with Marcus and disagree with Marcus around the idea of heterogeneous systems, where you take the best of each different platform and maybe combine them in some way. It would be great if that's how things turn out. A big challenge, though, is the transduction of quantum information from one physical platform to another. And a good example, I'll pick, just to dive into the detail for one moment and give it back to you. You could choose, let me come up with something, spin qubits. So that's a very popular platform in Australia. And if you look at spin qubits, they have many attributes that look favorable in which to build out a large scale machine. One of the big challenges, though, is that the density of those qubits, those things are tiny, and they need a lot of control wires that have to fit into a very small footprint. So, the size of a spin qubit is sub 100 nanometers, 20, 30 nanometers in terms of its squared, in terms of its footprint. And you might have 10 or something control wires that have to reach in there, which can be done in modern lithography, but those wires have to come out and connect to something in the macroscale world. And now if I have 1 million of these things and each has 10 wires, I've got 10 million wires that have to somehow fan out, okay? And this is not a showstopper, it's a big hurdle. Usually when you hear this kind of discussion at a conference, you'll hear, or read a paper, you'll hear a motivation, let's pull apart spin qubits, decrease that density to manage this bottleneck of I/O. When we pull them apart, we're going to couple them using superconducting resonators. Now you don't have a spin qubit. Now the thing is, actually you've bought into superconducting qubits, transmons, resonators, and all of the both advantages but disadvantages of that system. And so, we end up with a hybrid system that definitely combines some advantages, but also brings with it now the disadvantages of both systems. And, you can kind of play that out for a lot of different hybrid scenarios. And again, to kind of appeal to classical computing, there's something called Amdahl's law, which says that, whatever the bottleneck in the system is, it's usually referring to between a CPU and memory. You alleviate one bottleneck and then the next bottleneck appears, and when you start to look at these hybrid approaches, the bottleneck becomes your ability to have very high fidelity transduction between these different physical platforms interfaces. It's an area that's underdeveloped, but it's going to be really important, I think, before we start to be able to combine different systems. But the short answer is, it's early days.
So I really love something that all of you have kind of echoed in different ways, but you sort of, David, touched on it right at the beginning. And there was a phrase that you used that I could almost hear the same narrative that Kennedy used in creating a moonshot. right? This, in this decade, we're going to put a man on the moon. We don't know how we're going to do it, but we're going to do it anyway. And I think, there was a magic in what happened in that generation and in that time of this fundamental, bold claim, coupled very quickly with we don't know how we're going to do it, but we're going to do it anyway. And if we look at the spillover effects of what happened with, doing that, and with the moon shot and going to the moon, the flow over that spillover of technology into our lives and into, economic advantage for so many people and a positive impact on us, it's huge. And so I think that narrative of being, how do we do that for quantum, and how do we make quantum, because quantum is a more complex conversation than the moon, we're going to go to it, let's go. That is hard, but you can physically get everybody excited about it. And I feel like, again, it comes back to, we've got this amazing opportunity, I think, right now, where the general public is more engaged in science than they have been for quite some time, because of a pandemic, because of a vaccine, because of this shared need of a solution that can only come from discovery, that can only come from science and engineering, that can only come from, fundamental research being commercialized. It's a really exciting one to do if we can get this right for quantum. What can we become as a nation and also internationally? I do want to give a shout out to our audience participants that if you've got a question right now, it's the perfect time to pop it into the QA. It will come up on my little screen over here and I will ask you. I think what I might do is actually go to some of the questions that we have been asked already by our participants, and I'm going to throw these open to whoever wants to answer. So it's going to be a little bit of the case of, quick draw here and who can get there fastest. What do Australian businesses need to do now to be ready for our quantum future?
Yeah, so I might have a go at that one, Sally Ann. So what do they need to do right now? My suggestion is this. My suggestion is to right now observe what is being done around the world. What is being done by Army, what is being done by Boeing, what's being done by Airbus, what are being done by these big players who have already started doing this discovery process. Look at how they're doing that process and what are the results coming out of that process, and go, right, if we're going to do something similar, what would it look for us to do something like that? And it doesn't have to be big. So for instance, when Army started its quantum technology challenges, these were quite small, but because they were application focused, they got a huge amount of attention from the community, and very high quality people applied to that. And that really drew people out, because that's the number one question they want to answer. What can I use my technology for? So if you're a company in Australia, have a see what is going around the world and think about doing those challenges yourself. And if you need help, you can reach out to various places. But the thing I'd like to emphasize, though, is that this really needs support from a national strategic policy that invests in the infrastructure that allows companies to do this engagement, that provides places and points of call for people to engage with quantum computing, let's say through a national quantum computing facility or something similar, like we've seen established in the UK, the US and Europe, where it's a center or a focus of application developers, hardware providers, industry, defense, and it's a point of call for everyone to come to and engage in this process of application discovery. Anyway, that's my bit.
Thank you. David, Anna, did you want to add anything?
I'm happy to jump in, but Anna, if you do. I guess in this era we're in at the moment, one of the big challenges is how do you even navigate this complicated space? And what do you do when your competition comes out and says, our product is quantum enabled dishwashing detergent and or whatever it is, and all of a sudden you think, I don't even understand what quantum is. I can't tell you whether that's right or wrong, or how do you make sense of that world? How do you even ensure that the right option is to just do absolutely nothing and not find yourself in a difficult situation 10 years down the road? So, it's, of course, the usual story that quantum is coming and it's going to offer transformational opportunities for all businesses. That may or may not be true, irrespective of whether there are real applications for certain businesses. I think that it's going to be increasingly important to have an informed perspective as to whether it's relevant for your business, when it might be relevant for your business, why when your competition claims that they're all over it, that's also nonsense, and how to navigate that in a meaningful way. Very tricky, hard stuff. I think it's about connecting with those that do understand and have expertise, and leveraging that to some extent to better inform business strategy.
Fantastic.
I really don't have anything to add to that, because I was going to say that the most important thing is to understand and educate yourselves around how quantum computing can affect your business in the future, and whether that be by looking at what's happening overseas and what the army is doing, and perhaps running those challenges yourselves, or finding the people in your organizations who would be interested in learning more themselves as a stretch opportunity. That's what we found as well.
I think that's really great. And I actually like the parallels of, you actually kind of need to do both. Like you've all touched on that. So one is you need those people inside of the organization, if you just said, Anna, those technical people who are actually going to engage and go a little bit deeper and kind of see what the opportunity could be and really learn. But I think from that business perspective and that business lens, kind of recognizing that it is something you need to engage in and go, well, how do we think about that? Right now and in the future, and those two things might be quite different in terms of investment of time and people and energy, but really critically understanding it. And I think if I think about this was the same conversation we were having around AI and ML for the last sort of 5 to 10 years in Australia. Everyone's I remember at one point a whole bunch of businesses coming out going, we're AI experts, I've got 100 machine learning experts working for me, and I'm like, you absolutely fundamentally do not have 100 working for you, because the big tech companies have them in Australia, and there isn't 100 just sitting there waiting to be plucked, and you haven't hired them in 30 days or, the 33 months that you've been operating and trying to do this. You have a chatbot. It's great, but there's a gap. So it's a real space where there's, I think, a huge opportunity for growth, both technically, but also that application piece. We've got a really interesting question. I have no idea who's going to answer this one or what your answer is going to be. Is there a chance quantum computing will not be needed in the future if classical algorithms can be as fast?
Yeah, I guess the central premise of quantum computing is that it can outperform classical computers. And this is actually part of what quantum computing is doing. It is refocusing attention on the fundamental design of classical algorithms. So, I mean, if we're talking about the greater good, if the advent of quantum computing stimulates rethinking about classical computing such that it does outperform, then that's a win for everyone. So yes, I think that hits at the heart of what the premise of quantum computing is and the value it delivers.
I think it's a question really fundamentally about, computational complexity classes. And if you take, for instance, prime factoring, which is obviously a killer app of quantum computing, but should somebody wake up tomorrow with an efficient way of doing that classically, then that driver for quantum computing evaporates. There are classes of problem, though, where we don't know whether they live exclusively in one complexity class or the other, or whether that class is bounded by certain types of problems. So it's an open area of research. I think there likely are certain mathematical functions that one can say conclusively don't map efficiently into the classical world, but that doesn't close the door to alternate approaches that are still classically based. Yeah. I think that's always true.
Great. There's a really interesting one that's just been popped in. Other than drawing parallels to other industries, how do we identify business problems which are likely candidates for being solved with quantum technology? So that tells me that we probably still haven't quite given people quite what they're looking for in answering that question. So what do we do to help them identify them? I'm going to say that we have to sign them up to some of the courses or some of sessions that you guys run or something like that. But what else can we do?
So I might have a go, Sally, but I think Anna would probably like to have a go at this one too. So I'll have a quick go and then pass it over to Anna. My experience through both Quantum Brilliance and the Army is that there's a few fundamental ideas you have to get right about quantum computers. So, and where advantage lies with quantum computing. So the first thing is quantum computers won't make things that are already faster. So if a process or something is going really well at the moment, a quantum computer won't accelerate it. What it might do is it might make it more accurate within the same amount of time budget. So that is a possibility. The other thing to acknowledge is that currently quantum computers, I'll abuse the term, have a slower clock rate. So that means the turnover of a quantum computation is slower, but because it can do things much more efficiently, it can tackle much larger problems or much more difficult problems within that time. And so that's what can give you that dramatic speed up, because instead of doing 1,000 turns of the crank, you only got to do a couple of turns of the crank to solve the problem. But that also means that you're not going to make fast things faster, because the crank fundamentally is turning at a lower rate than a classical computer. So that's that idea of fast things won't go faster. Challenging and difficult things will be fundamentally much faster or much more accurate. And that is then how to think about, okay, well, that means that I might have to completely rethink how I do computing. So in the past, I've made choices not to do that way because it's been hard on a classical computer. And as a result, I've had to introduce all of these approximations, all these other routes to get to the same endpoint. Now, quantum computers give you an opportunity to rethink your workflow. And instead of making this choice, you can now make a brand new choice and go this direction and therefore get a better result in the end. And the sorts of problems you can think about are things where, certainly in the near term, is where there's a combinatorial explosion. So where you have to either think about many options or work through many possibilities, and a classical computer is forced to just brute force go through that. Those sorts of combinatorial explosion problems is where quantum computers are currently offering a bit of advantage. And for example, that's in quantum chemistry, where you've got all possible solutions of a molecule and you've got to work out and crank through that. But you could also do the similar in portfolio optimization, logistics optimization, or even signal processing. There's certain problems where that ability to think about many combinations and sort through it efficiently is important. So that's my experience so far.
Anna, did you want to add to that?
Yeah, so we've actually found this one kind of a really difficult question to tackle, because if you think about it, most people don't really understand how a classical computer works, let alone a quantum computer. So figuring out what problems are good for a quantum computer is really thinking about the difference in how those two types of computers compute, and then looking at the problems which fall between them or fall in one gap or the other. So that's like, in a forum like this, you can't really like give people a simple answer. Then you know, Marcus has done a really good job in talking about the types of problems that quantum computer we're looking at with quantum computing in terms of the combinatorial explosion of possible possibilities. But that really doesn't, like, you know, if you think about it, that it's hard to explain why quantum computers can be good at that without explaining how a quantum computer works and then explaining how a classical computer works at the same time. But yeah, I think I like to explain like some of the earlier the more near-term interesting areas that quantum computers look like they can be useful are in problems that look like quantum computers, right? So if like quantum chemistry, quantum physics, trying to understand nature better is sort of a natural area because quantum computers work in a different way naturally. And then how do you extrapolate those types of problems to more obvious business problems is the harder part.
I'm seeing a whole new need in sort of both our tertiary and our education system for people, not necessarily to become quantum physicists, but to actually understand this problem and be learning about it right now in their computer science and their software engineering degrees. And, all of those kind of places, so that they are actually thinking about it. Because what I've just kind of really, if I kind of extrapolate out what I've heard from both of you just saying then is, actually like really reevaluating and thinking about the processes that we do run and thinking about those gaps and where it is in between. It's almost like a whole nother way of like unlearning to relearn, and to relearn which one is one way and which one is another way. And there's a nice question that kind of came in, which I think is, it's going to be my second last question to you, but I think I'll stick with you, Anna, on this one first. Is, how do I prepare my kids for quantum computers, assuming that by the time they're ready for their careers, quantum computers might be pervasive? And I think that's almost what we're getting at. But if I hear it right, it's probably not an either or. It's a case of both. And so how do you think about that? Because I think this flows on from the conversation we're just having.
It's actually, I think for kids, it's actually much easier because they're just really interested in learning about anything and everything, as long as you can keep it interesting and keep their attention. So in that space, there's lots of interesting little games that you can learn about quantum physics and quantum computing these days. And learning about how technology works and keeping their interest in that area as they get older is sort of the harder part.
Marcus, David, did you want to add anything to that?
Yeah, so I actually think the children are the answer to our problem. And that is that when we're thinking about designing quantum algorithms right now, many of us struggle. It's a very hard task. And we either use rules of thumbs or we ask a classical computer to basically generate the algorithm for us. And if we can nail a way to enable children to think differently to us, then we may be able to get a chance where they can much more efficiently and much more intelligently create quantum algorithms that make use of these quantum phenomena to solve problems. But I don't know how to do that.
I love that. So basically, answer to this parent out there that's asking for their kids is, get them engaged now, because Marcus, might want to work with them. Don't wait for them to grow up.
Exactly.
Look, we are almost at time. I've got one question for all of you that I want to do to wrap up, because I do think, like, I've learned a lot today. I feel a bit better prepared for a barbecue question now. Not well prepared, but a bit better prepared. I think a lot of people on here have learned something, and they're certainly engaged and they've stuck with us through this hour and in hearing about it. So if there's one thing, my final question, I'm going to go down the line as I see you on my screen, which is probably nothing what the video is or what anybody else is doing is, but I'm going to go Marcus, Anna, and then David. If there's one thing people can do after today's webinar to get engaged in quantum, what can they do?
One thing. So as I said earlier, take a look at what others like you are doing and see, and then extrapolate to yourself.
Awesome. Thank you. Anna?
So I have to put my IBM hat on and say that you should go to the IBM quantum computing, where you can actually learn about quantum computers and program real ones that we have cloud accessible.
Great. We will make sure that we get that link and pop it into the follow-up for everybody that attended today. Great. David?
Similarly, I would point anybody to Microsoft's tools that allow you to play with quantum algorithms and write code for yourself. But in addition to that, this is also about embracing and being involved in science, mathematics, and big ideas. And I want to just make the point that if you're interested in being part of this journey, I mean, in some ways, the question is a little bit more geared towards what happens when a quantum computer switches on. We're not there yet. If you want to be part of the journey and you understand classical computers or electronics or how to solder or how to, work with regular science, not quantum science, we need plenty of that too. And there are many opportunities in Australia to engage in all of the science and engineering, which is very broad. And you may already have those skills to become part of the journey in building this technology.
Awesome. Thank you very much. I'm just going to, as we wrap up today, invite Michael Harvey from EQUS to just give us a quick wrap up and a few closing remarks about what he's heard from the panelists today. So over to you, Michael.
Sure. Thank you, Sally. Look, I want to thank the panelists who have been very generous in giving us their time and insightful conversation around this topic. Anna from IBM, David from Microsoft, and Marcus from Quantum Brilliance. I certainly feel like I've learned something here today. And one of the takeaways that I'd like to add to what our panelists have said is, if you have an interest in quantum computing, one of the best ways to carry that forward is to just dive in. There are many resources available on the web from our panelists' companies and from others that let you learn about this and try it for yourself. So I'd definitely encourage the audience to dive in and try it out. I want to especially thank Cicada Innovations and Sally, our wonderful moderator today, and just end with a couple of words about EQUS. So we at the Centre for Engineered Quantum Systems are more than just about academic research. Our objective, what we aim to do, is to deliver economic, environmental, cultural contributions to the whole of Australian society through taking our research and focusing on how we can translate that and the new knowledge that we develop into quantum technologies and applications that prove useful for our industry, business, our everyday lives throughout Australia. So it's events like this one today. We're trying to build up a culture of innovation, translation, commercialization amongst our quantum scientists, amongst our researchers, and amongst the businesses and people that we interface with and are going to affect with our outputs. So please visit us on the web if you want to learn more. And with that, it's back to Sally.
Thanks so much, Michael. It's really great to have your support and collaboration. And I just want to echo those words. I think the power of what we have been talking about today, and I think what all of our panelists and what you want to see at EQUS is this collaboration. It's actually bringing people together from research and academia and industry and community to actually point at a great big moonshot. Maybe it's not a moonshot, maybe it's not a Mars shot, but to point at the challenge and the opportunity and say, let's go in that direction and see what we discover, and let's do it together. Because I think that's the reality, particularly in something so ambitious as this. It is only when we do that collectively and we do that together where we're actually going to see the breakthrough and the opportunities and the things on the other side of it. So it's a really powerful reminder that we do need to collaborate and come together. I really do want to thank our panelists today. Thank you so much for your time and your generosity of your time and your wisdom and being patient with the noobs out there, including myself on quantum. This is my second quantum conversation that I've had to facilitate, and I won't pretend that either one of them is easy, but I always go away having learnt something and thinking about it differently. And for me today, the particular thing that I'm going away thinking about is actually that last bit of the conversation that we ended on, which is thinking about the difference between classical computing and quantum computing and re-architecting how you're thinking about things and what might be suitable for one and what might be suitable for other. To be honest, I hadn't actually really thought about that. I don't know why. It seems such an obvious thing, but it's only in conversations like this that sometimes the obvious becomes, visible to you. It's been there all the time, but you haven't seen it. So I want to thank you for your wisdom and your time and your commitment. Big thanks to all of you who've joined us today, for giving up your time and to submitting your questions and helping us shape our discussion. Big thank you to our sponsors at EQUS and AusQuantTech. Please check out their websites and get engaged with what they're doing. It is a space where you need to sign up and be part of the conversation and come on the journey with all of us. And if you want to know more about the events that are coming up for us at Cicada Innovations and the things that we'll be doing with our collaborators, please sign up to our newsletter. We always love to share what our partners and our collaborators are doing, like EQUS and other, and we will continue to share their events and the opportunities to engage with them. So connect with us and we'll connect you with the deep tech community all across Australia and internationally. Thanks for joining us. Bye.